Okay, everybody, we're going to work a couple force of gravity problems. This is the equation that we have been using in class. We have that this is the force of gravity. I don't actually have that up here, but we could add it. F, you should already know, is a force. So in this case, we're going to make it force of gravity. Forces are measured in newtons, and this will be 2. We have that F, the force of gravity, is equal to capital G mm over r squared. The big G is the gravitational constant. We find that on our reference tables. I went ahead and wrote the number right here on the paper, 6.67 times 10 to the negative 11th. The 2 m's are masses. They need to be measured in kilograms. And then we have r, which is a radius, in meters. The first example problem, which we have already worked these if you're in my class, says, what is the force of gravity exerted on a 70-kilogram astronaut standing on the Earth's surface? Well, if you're standing on the Earth's surface, if here you have a little stick person standing on the surface, the radius of the Earth is listed right here, 6.38 times 10 to the 6 meters. So that's the radius that we're going to use. It's the distance from the person to the center of the planet. And then you've got the mass of the Earth. We have the mass of the astronaut. So here's our R. Here's one of the M's. Here's another M. And what it wants is, what is the force? It's wanting F. If we plug this into our equation, I'll rewrite it for the sake of simplicity's sake. We're finding F. G is coming from a reference table, or for us right here off the page. 6.67 times 10 to the negative 11th. One of our masses is 70 kilograms. It doesn't matter which one goes first because it's multiplied, so we can move them around. And then the other mass is going to be the mass of our Earth right here. 5.98 times 10 to the 24th kilograms. I'm kind of taking some shortcuts here and not writing the units in, but you could totally do that to keep track of them. Now our radius is 6.38 times 10 to the 6, and that number is squared. And if you work all of this out and you do your math properly, not forgetting to square the bottom one, you will get an answer of 686 newtons, which has the proper number of sig figs for the numbers that are in our problem. Okay, I'm going to skip down here. I'm not going to work everything, and I'll work example 2. What's the force of gravity acting on a 70-kilogram astronaut who is at an altitude of 6.38 times 10 to the 6? Well, in this case, this person, instead of standing right here on the Earth, is actually up in the air. So this person this is the same number we used up here as the radius of the Earth. If I pull this down, those numbers are identical. So in other words, they're at R, and then they've got R again. They're at 2R, double the radius. So when I go to put this into my problem, I've got to remember to double it. So G is still 6.67 times 10 to the negative 11th. We still have a 70-kilogram astronaut, and we still have an Earth that weighs the same mass as before. I'm getting that number from the previous problem. But my radius this time is double the 6.38 times 10 to the 6. Now, here's the thing students mess up. You have to square it with that 2 inside. You can't make it 6.38 to the 6 squared times 2. The 2 needs to be squared as well. And if you do all of that and plug it into your calculator properly, you will get an answer of 171 newtons. You can always pause the video and see if you get that. Now, in class, I made my students work these problems at the bottom that really aren't all that difficult. It's maybe hard to set up and figure out how to do it the first time. The first one says an astronaut weighs 800 newtons on planet X. How much would she weigh if she was at an altitude equal to the radius of planet X? The issue is that there's not enough numbers. What I do know is this: if she weighs 800 newtons, I know that that has to come from G-M-M over R squared. So I'm just going to leave that right there, and I'm going to set it up again. It wants to know how much would she weigh. Well, remember, weight is a force. weight is the force of gravity on your mass. So it wants to know how much she would weigh, that would be this F, if she was at an altitude equal to the radius of planet X. Well, what that would do, it would be just like this problem up here, is if she was at the same radius as an altitude, it would make it 2r. So G is still the same. The mass of the girl and the mass of the planet haven't changed. As you can tell, I'm recording this in third period and classes are changing. What's going to go down here is double the radius. We're going to square 2 times r, just like we did in this problem up above. My next thing is going to be to distribute this, like to actually work some of it out. GMM I can't change. 2 squared would be 4, and r squared would be r squared. Well, if you look right here, I'll use a red here. Right here is GMM over r squared. Well, I see the same GMM over r squared right there. Like, whatever, this number was 800. So this number right here is still 800. What I end up with the number is I end up with basically 1 over 4. This 4 on the bottom tells me that my mass is going to end up decreasing by a factor of 4. So it would really come out to be 1/4 times 800. Well, 1/4 of 800 is 200. So on this planet, my girl would weigh 200 newtons. Let's try it again. We have the spaceship this time, and a spaceship that weighs 10,000 newtons. So same idea, I've got 10,000 newtons. I don't know anything about it. I don't know the mass, I don't know the radius, I know nothing. So I'm going to set it up again to this same equation, GMM over r squared. I'm not squaring the m's because they're not necessarily the same. It wants to know how much the spaceship would weigh if it orbits a planet twice as massive, right here's part of what I need, and half the radius. So we're going to find the force of it if we change some of these things. Well, G doesn't change. I'm going to make the first M maybe the spaceship, like the weight of the spaceship. The mass of the spaceship won't change, but the weight will. I said weight to start with, sorry. The mass won't change, but the mass of the planet is going to be 2m. It gets to be twice as massive. So I'm going to double one of them.
If you're in Mr. Stetzer's homeroom, please make your way to the gym lobby for the choice bus. If you're in Mr. Stetzer's homeroom, it's your turn to go to the choice bus.
Sorry for the interruptions, I didn't think about this. Okay, for the radius, it's half of the radius. So what we're going to do is put in half r, and then that gets squared. Next thing I need to do is I need to work the numbers out of it, okay? I'm going to move this 2 over to the front so that it's 2 times GMM, okay? Underneath it, 1/2 squared becomes 1/4, and then that's r squared. And once again, do you see my GMM over r squared from up above? What that in essence does is it says 2 divided by 1/4 will be multiplied by 10,000. And how do I know that? Because GMM over r squared is 10,000. I'm just going to substitute that in down here. If you do, you can do 2 divided by 1/4, that's 8. 8 times that becomes 80,000.